we discussed about the equilibrium. So equilibrium is actually a state of uh, anything in which we take the resultants zero. In the equilibrium, this is a state of any body, any object in which the resultant forces in any direction is zero. Forces are zero Newton, and the second thing is the resultant moments. So resultant moments are also zero. So we can write here moments, resultant moments are zero, and as we know that moment unit is Newton meter, so resultant moments are zero. So actually, what's the meaning of resultant moments zero? What's the meaning of the resultant force is zero? In the simple way, we can state as the resultant moment is zero, then the sum of clockwise moments and uh, the sum of clockwise moment and sum of anti-clockwise moments are equal. Like moments in the clockwise direction moments uh, is equal to anti-clockwise moments. So this is the meaning of the resultant moments that are 0 Newton meter. So when we simplify many problems in which we can have the rigid bodies, so but we choose a point, any point to take the moment about which point we are taking the moment. As if you remember, if we discussed in the last class, we have a case, we have different cases in which we find out the moment about a specific point. So the same thing we have today, like we find out the moments about the specific point. For example, we have the case for this rigid body, and we want to take the resultant moments. Let's say this is a point S, so we can find out the moments about this point. So this is the necessary thing to take a point, to choose a point about which we are taking the moments. So we can solve the exercise that are different types of question we have related to this, and we start the exercise 4C from applied book, and this is in the first question we are given different cases in which AB is a uniform rod of the length 5 meter and weight 20 Newton. Length is 5 and weight is 20 Newton. So 5 meter and weight is 20, weight 20 Newton. In these diagrams, AB is the resulting in the horizontal position on the spot A and C. Let me draw the figure. Uh, this is the point A. This point is C. This is D, and this is the point B. The values that are given here, this is 1 meter, this is 3 meter, and this is again 1 meter. So here we have C and D spots. In each case, find the magnitude of the reaction at C and D. Magnitude of the reactions at C and D. So let's take uh, give me a second. Okay. C and D, about C and D, so we can take C point resultant about C and resultant about D. So RC resultant about C and resultant about D. So weight is 20 Newton, that is in the downward direction. That is mg actually, and this is equal to 20 Newton. This is given. So resolving vertically, because the two forces are in the upward direction, the resultant, and one is the in downward direction, that is the weight. So anti-clockwise and clockwise or opposite forces we take equally for the equilibrium. So RC plus RD, this is equal to 20 Newton. And taking the moments about C, we this is the vertically resolution. So when we take the moments about C, so C is uh, 3 multiply by 3 is the given, that is length, sorry, 5 is the total length, so 3 is the length, that is this one. So 3 multiply by RC, this is equal to in the downward direction, as weight is in the downward direction, so this distance will be 1.5, this is 1.5. So for a weight we take the distance 1.5 multiplied by the weight is downward, so 20 value is this. So now look at the this is equal to 30, 20 times 1.5, this is 30. So we can write R, oh one, here we are taking about moments about the C, so we take here because about C we take RD. So RD is equal to 10 Newton, and RC will also be 10 Newton because weight they are equidistant from the weight is equidistant from the RC and RD. So this RC will also 10 Newton, and the distance is same. So this is the resultant. This is the magnitude of the reactions. Reaction about C, reaction about D. So in the same way we can solve the point. As you can see that we are taking the moments about some specific point. Here we are taking C and D, so you can find out the reactions, magnitude of the reaction. We are not involving the directions here. We solving according to the directions, like two are reactions of C and D are in the upward direction and weight is in the downward direction, but signs are not included here for now because we are just talking about the magnitudes. Now let's practice the question number 2. In this question, each of the diagram shows a length rod, light rod, in equilibrium in a horizontal position under the action of set of forces. There are set of forces here, like more than 2, 3 or 4, 5 types of forces we have. Find the values of the unknown forces and distances. Okay, let me draw the given diagram. In this, the diagram is this is 10 Newton, this is 15 Newton, this is Y Newton, this is unknown, this is X Newton, this is again unknown, this distance is 1 meter, this is 2 meter, and this one is 1 and this one is 1. Total is 2, and this distance is 1 meter. So we find the values of unknown forces and distances. So here the forces are unknown, so we can find out the forces. we resolve vertically, then we find out the moments about some point. So let's take the point, let's take this as the point P. In the previous question we take the point C, and we involve this one. So here we are taking the point P, about which we find the moments. So first of all, we resolve vertically. So vertically resolution is vertically x plus y, the upward direction, two forces in the upward direction. Anti-clockwise movement is equal to clockwise movement. Sum of the anti-clockwise movement is equal to the sum of anti-clockwise movement. So 10 plus 15, that are in the downward direction. So this is x plus y is equal to 25. Now we what moment about P. Moment about the point P. So moment about P means that 15, the downward force, multiply the distance of the 15 from the point P. 2 plus 1, you can see the figure, 2 plus 1, the distance of this force from the point P. This is equal to 10 Newton force. Now take the distance of the 10 Newton force, that is multiply by 1 meter distance from the point P, and add the other force, that is plus sorry, the other one is y, about the like we are taking about the point P. So there are three forces, three moments which we take here. We take 15 Newton, then 10 Newton. Now we are taking for y. So y multiply the distance of y force is 2. So very simply this is 45 is equal to 10 multiply by, sorry, add 10 plus 2y. So y is equal to 45 minus 10, 35 divided by 2. This is 17.5. Y value is 17.5 Newton. 17.5 Newton. Now put this value into the equation. X plus y is equal to 25, and we get the value of y. We get the value of x. When we subtract 17.5 from 20, this is x, that is 7.5. So this is how the simplest thing that we have here. We need to add the clockwise moments and put them into the equal to the anti-clockwise movement, the first thing. And then we should know about the resolve, how we can resolve vertically, and how we can take the moments about some specific point. This we discussed in detail in the last lesson, where we find out the moments about some specific point. So now let's practice one more question. Uh, like okay, we solve the next question then. Question number 3 is theoretical but easy. In the question number 3, Jack and Jill, the case we are given. Jack and Jill are playing on a seesaw made from a uniform plank AB. Now let's draw a plank AB. Let's take this is a plank AB. And the length of the length 5 meter pivoted at M. Now the length, total length is 5. So we can take the total length 5. and the midpoint of AB. M is the midpoint of AB. So let's take this is M. Now Jack has a mass 35 kg. So mass 35 kg and weight will be in the downward direction. So as this is the AB, for example, this is the Jack and 35 kg, 35 G, this is the weight and it is in the downward direction. Now Jill has the mass 28 kg. Now this is the Jill and this is in the downward direction and 28 G Newton. 28 G. G value is 9.8, we know that. And Jill sits at A as we draw, and Jack sits at a distance x from the B. So distance x from the B. So this is the point B. So this is the point actually. This is point B. This is point A. So this distance is x. We need to find this distance. And plan, the plank is in equilibrium. Find the value of x. As this is the midpoint, so this distance will be 2.5, like from here to here, 2.5. This is also 2.5, but this is the x distance because total is 5 meter and this is m midpoint. We can find out the value of x. So clockwise movement is equal to anti-clockwise movement. As you can see that 35 kg is 35 g weight is in the downward direction. So uh, 35 is heavier than 28. So one move in the downward direction and one move in the upward direction. So now take the clockwise and anti-clockwise movement. 35 moves in the downward direction. Weight is downward. Both weights are in downward direction, but due to heavy weight of the 35 G, this on the 35, this is 35 is the mass of Jack. So Jack move in the downward direction and Jill move in the upward direction. Just like uh, one object is heavier and one is light object, and we this is in the equilibrium position. Equilibrium not means that they are at the rest position, they balance each other. Equilibrium means that the sum of their moments simply equal to 0 Newton. So this means that clockwise movements is equal to anti-clockwise movements. So clockwise movement for 35 kg we take 35 and the distance of 35 is 2.5 minus x. You can see the figure. This is equal to 28 and the distance of 28 g is 2.5. So when we divide we can divide by 7 both sides, then it is 5. 2.5 minus x is equal to 7 divided by 28. This is 4 multiplied by 2.5, and g both sides cancel each other. So this is, now we can resolve for x. So 5x is equal to, I'm writing directly, this is equal to 2.5 into 5 minus 4. x is equal to 2.5 divided by 5 and x is equal to 0.5. Now we can find out the we are finding the value of x, so this is the value of x, 0.5 Newton. So we can say that the the jack is 2 meter from the point M. You can see the figure. The jack is 2 meter from the point M and the distance of jack is 0.5 meter from the point B. That is the value of x. Now look at the next question. That is up 4, but one sec. Question 4 is same as it is. Anti-clockwise movement is equal to. Question 5 is also same. Now we look at the question number 6. This is interesting and lengthy somehow. Okay, question number 6 is a uniform rod AB. So we draw a rod AB. Now of the length 4 meter. So the length is 4 meter. Total length of the rod is 4 meter. Weight 20 Newton. So weight of the rod is in the downward direction, that is 20 Newton. Is suspended horizontally by two vertical strings attached at A and B. So two vertical strings are these strings, and this is tension in the string A, tension in the string B. These are in the upward direction. Now a particle of weight 10 Newton. So a particle is here that weighs 10 Newton. Is attached to the rod at the point C. Now let's take this is the point C, where A and C is 1.5. A and C is 1.5. So I can draw the distance, this 1.5. And find the magnitude of the tension in the two strings. So if this is 1.5 and 20 Newton weight of the string is at the middle, so this distance is 2 meter and this distance is 0.5. Okay, magnitude of the strings. So T, tension in string A, tension in string B, we have written. So we write the vertically resolution. So tension in the string B, that is in the upward direction, tension in the string A and B in the upward direction, this is equal to the two weight that are downward, so 10 plus 20, so this is equal to 30. Now let's take the moment about the point A. So we are taking the moment about A. So other than A, there are three forces. So first take the 10 Newton force. 10 multiplied by the distance of 10 from the point A is 1.5. So plus, now take the 20 Newton, 20 Newton multiplied by the distance of 20 Newton is from 1.5 plus 0.5. This is equal to the other, that is distance of the tension B is 4. 2 plus 2 is 4. 1.5 plus 0.5 plus 2, this is equal to 4. So I multiply with 4. So this is the moments about the point A. So for TB is equal to, tension in the B is equal to 15 plus 40. Now TB is equal to 40 plus 15, 55 divided by 4. So this is 13.75 Newton. Now put this into the uh, vertically resolution equation that we have found it. TA, tension in the string A, plus TB is equal to 30. So 13.75, TA is equal to 30 minus 13.75. So this will be equal to 16.25 Newton. So these are the tension in the string A and in the string B. So now the B part of this question is, the particle is moved so that the rod remains in the horizontal equilibrium with the tension in the string B is 1.5. Now the value of TB is given. This is the B part. This is 1.5. 1.5 times to the tension in the string A. Find the new distance of the particle from A. Now we need to find out the distance. So particle is now, we need to draw the figure again because the distance is changed now. This A, this is the string A, this is the 10 Newton that is at the new position, that is C prime. First it was at the C. This is a 20 Newton. This distance is not given now. Let's take this is X. The total distance is 4. We know that this distance is, this is the tension B, and tension B is 1.5 times to the tension A. So if this is T, then this is T, 1.5 T. This is the point B. This distance is 2 meter. Now as beam is in the equilibrium, so we can resolve vertically in the same pattern. Tension in the string A plus tension in the string B, this is equal to the downward weights 10 plus 20. Now 2.5 T is equal to 30 and tension is equal to 12. Now we can take the moments about the A, about the string A. So 10 Newton multiply the distance of 10 Newton weight from the point A is X. So multiply with X plus, now take the 20 Newton weight, distance of the 20 Newton weight is 2 from the point A, and this is equal to, the third one is the 1.5 multiplied by 12. 12 is 1.5 times 12, sorry, 1.5 times T, so T value is 12, so I just put the value of 10. So multiply this with the value of the distance that is from the A, so distance is 4. Force multiplied by distance, simply we are taking this, so we can resolve this for X. So X is equal to 10X is equal to 72 minus 40, and X is equal to 3.2. So this is X is the distance, new distance of the particle from the point A. So you can see that we are finding the equilibrium, we are taking the equilibrium position, equilibrium state, and we are finding the uh, finding the moments, resultant moments, and we are resolving the vertical and vertical forces, and then we find the moments about some specific point, then we can find out the value of unknown length and unknown forces. In the same pattern, we can solve the next question 7. Okay. In the question number 7, a uniform beam AB. Let me draw the beam here, A and B. This figure is actually given. So length of beam is 5 meter. So this is 5 meter. Mass is 60 kg. Has a load of 40 kg. Attached at B. It is then held horizontally in the equilibrium by the two vertical wires attached at A and C. You can see the figure. The tension in the wire at C is 4 times as the tension in the wire at A. So if the tension in the A is T Newton, then the tension in the C is 4 times to the A, so this is 40. Two weights are attached. So let first take this is the 60 G weight, and one weight is attached at B, that is the 40 G Newton. Now look at what is uh, by modeling the beam as a uniform rod and the load as a particle, calculate the tension in the point C and distance CB. CB, let's take this distance is X that we need to find out, and the tension in the wire C. Now it is easy for us because we draw the figure. Now we can easily resolve. Now let's take the vertically 4T plus T, two upward direction forces is equal to downward for weighter forces, so 40G plus 60G 100G, and this is 5T, so T is equal to 20G. So this is the tension in the A. Now the tension in the C is 4 times, so 4 times means that 80, and the G value is 9.8, so 9.8. So 784 Newton is the tension in the string C. To find out the unknown distance, we can resolve the moments about some specific point. Let's take the point B. So moments about the point B. So about the point B, other we have 3. So first take 20G. 20G means that tension in the string A, that is 20G. Multiply the distance. Distance is 5 from the B point, plus 80G, that is in the upward direction. 80G means that tension in the string C. Multiply the distance. Distance is X. This is equal to the downward weight, that is 60G, multiply the distance, that is 2.5, because the 60 kg mass is exactly at the middle point, so 2.5 from the point B. Now we can resolve this is 5 plus 4x when we divide with 20 on the both side, and 5 plus 4x, so let me draw it down, 5x 5 plus 4x, and this is equal to 7.5. So x is equal to 2.5 divided by 4. So when we find this value, this will be 0.625. So the distance of the CB distance is 0.625 meter. So this is the question 7. I think uh, we can practice one more. Question 8. Okay, question 8 is easy. Question 9 is also easy, same as the previous questions. You will practice this. I'm solving now, but question 8 you will practice question 8. I'm doing question 9. This is a figure in which that is given in the question 9. Oh, okay, one sec. Beam is in the equilibrium, uh, and this is actually the same type as the question we have done now. This is the point B, this is the point C, this is the point A. This distance is 4.5. The total distance is 8. So we can take the moments about A. A weight is in the downward direction. That is the given data in the question. So weight is in the, that is exactly from the middle point. So this distance is 4. This distance, this tension in the string TC, this is TA. Now taking the moments about the point A. So 4 point this okay, this is 30. Our weight is attached, that is 30 Newton. So 4.5 distance multiply the force is TC. We are taking the moments about the point A. Then 4 distance of the weight W. This is W. Plus 8 distance of the 30 Newton weight. So TC, we can write the 4.5 as 9.2. So 9 is equal to 8 multiply 2 on the both side and 9 TC. So TC is equal to, divide the 9 on the both side. So 8 by 9 W plus 160 by 3 when we divide with 9. So this is the A part of the question 9. Now to find out the value of W, you can resolve the